Hey guys, how's it going? Today we're going to talk about Chapter 8. And the first part of Chapter 8 is what we're going to talk about are what are called factors and the GCF or the greatest common factor. Last chapter we talked a lot about multiplying, and we multiplied different things together to make a whole. Well, now we're basically doing the opposite. We're breaking them up into what multiply together. So the first we want to talk about is prime factorization. If you remember what prime numbers are, okay? Prime numbers are numbers that can only be divided by one itself, right? So 2 is a prime number, 3 is a prime number. 4 is not because 2 times 2 is 4. 5 is a prime number. 7 is a prime number. 6 is not because 2 times 3. 8 is, 2 times 4. 9 is 3 times 3. 10 is not, 11 is, 13 is, those kinds of things. We can keep going. But our goal here is to say what numbers multiply together to get 60, okay? And there's a few different ways to do this. Now, the ultimate goal here is to only have prime numbers, okay? Because we could say 60 is 2 times 30, right? But that's not going to be prime factorization because with 2 times 30, 30 is not a prime number. So we're not done yet kind of thing. So that's the goal. We got to come up with what numbers multiply together to get 60, and they're only prime numbers, okay? So there's a couple different ways to do this. My favorite way is what we call a factor tree, okay? And basically, we make a tree and we say what numbers, and it really doesn't matter what numbers you use here. But basically, you just ask the question, what 2 numbers will multiply together to get 60? Okay, we already said 2 times 30 will work, okay? And then you just look at the next branches. 2 is a prime number, so you're done with that part of the tree. And now you go to 30, and you say, all right, what 2 numbers multiply to 30? And there's lots. We could use 2 and 15. We could use 6 and 5. It truly does not matter, and I'll show you that in a second. So let's say we used 5 and 6, okay? Well, again, we look at the ends of the branch. So the 5 is prime, so that's done. The 6 is not, so we got to take the 6 a little bit further, okay? And the 6, what 2 numbers multiply together to get 6? Well, that's 2 and 3, okay? So what you do now basically is, this is what we call a factor tree. We only look at the leaves of the tree, okay? What I mean is this 6, I call this 6 or this 30 a branch, because the branch got broken up. We can basically ignore all the branches of the tree. All we need to look at here are the leaves of the tree, the endpoints, okay? And basically, what do we have? We have a 2, we have another 2, we have a 3, and we have a 5, okay? Basically, we have 2 2s, 1 3, and a 5, okay? That would be what we call prime factorization. And I said earlier, it doesn't matter what 2 things we use. First one we used 2 and 30. Well, if we wanted to, we could have used 4 and 15 because 4 times 15 is 60. 4 breaks down, that breaks down into 2 and 2. 15 breaks down into 3 and 5. And what do you know? Again, we don't have to worry about those. Those are the branches of the trees. We just look at the endpoints. We have 2 2s, 1 3, and 1 5. The same answer, okay? So it doesn't even matter what method you use. You just look for any 2 numbers that multiply together to get 60. So doing factor trees is one method of doing this. That's my favorite method. Another method, it's called the ladder method. Ladder method, okay? And basically, you kind of do the same thing, but you just say we have this 60. What number can you divide this 60 by? Well, we could divide that by 2. Okay, so we do that division and we get 30. All right, 30 is not prime. What can you divide 30 by? Well, we can divide that 30 by 3. In the numbers that you're looking to divide by, you want them to be prime. That's the one thing with this that I'm not as big of a fan. Over here, it doesn't matter. You don't have to use prime numbers because each part can get broken down. Over here, you have to remember that the numbers that you're dividing by have to be prime numbers, okay? So we do that, and we get 10, right? So we divided the 60 by 2. We divide the 30 by 3, and we look at the 10 and go, all right, what can we divide the 10 by? Well, we can divide the 10 by 2, and we get 5, and then 5 is a prime number. So what do we have? We have 2 2s, 1 3, and a 5, okay? All your answers are out here. The ladder method is a very good method, but there is one simple problem that people make, or there's a mistake people use with the ladder method. And that would be when they do that, they don't use prime numbers to divide. And they say, all right, well, let's divide by 10, right? Well, when they do that, divide by 10 is 6. You go 2 here and you get 3. Well, now it looks like I only have a 2, a 3, and a 10, right? Well, where'd the rest of the answer go? I'm missing a 2 and I'm missing a 5. Well, that 10 is where the other 2 and the 5 are located, okay? So this is a common mistake that people will make with the ladder method. It's correctable, but it's something that you have to be very careful with the ladder method. That's one of the reasons why I like the factor tree method a little bit better, because you have to worry about the numbers that you're breaking them down into. Are they prime or not? Because if they're not, you just keep going, okay? So I'm going to kind of stick with the factor method. But this is what we call prime factorization. We want to get it to this point, okay? And then the way we write our standard answers, as you've seen, is we go in order, right? The 2 is the smallest, the 3 is the next, the 5 is the next, and so on and so on. And it's easiest to use the exponents of how many 2s do you have, how many 3s do you have, how many 5s do you have, okay? So let me try just another example here. How about 72? Well, what are any two numbers that can multiply together to get 72? Well, I know 72 is one of my multiples of 9, so it's 9 times 8, right? Well, 9 can be broken down. 9 is broken down into 3 and 3. 8 can be broken down into 2 and 4, right? 2 times 4 is 8. 3 is prime, 3 is prime, 2 is prime, 4 is not. I can take that 4 a little bit farther into 2 and 2. And again, all we need to look at are the leaves of the tree. We have a leaf here, here. We don't have to worry about the 4 because the 4 got broken down. We don't have to worry about the 8 because the 8 got broken down. But here's a leaf of a tree, here's a leaf, and here's a leaf, okay? So here's our answer right here. And then we just look, how many 2s do we have? Well, we have 3 2s, and we have 2 3s, okay? 1 2 3 2s, 2 3s, and we're done, okay? Simple enough. So now we talk about what is known as GCF, or the greatest common factor, okay? And basically, a factor, again, is just what are all the numbers that you can divide by, okay? So there's 2 methods here. One method, it's a good method, but it's an easy one to make a mistake here. And that is basically just saying, what are all the different numbers that multiply together to get 24? Well, you could multiply 1 times 24. And I like to write them like this, okay? Where what is the way you can multiply together to get 24? 1 times 24. You could multiply 2 and 12 together, okay, to get 24. You could multiply 3 times 8, okay? And then you can multiply 4 and 6 together, okay? So basically, that means every single one of these numbers are factors of 24, because you can divide 24 evenly by every single one of those numbers, okay? But they are factors, okay? So we're just looking for what is the biggest common factor that they have in common, okay? And then 60, we would do the same thing. What are all the different ways you can multiply together to get 60? Well, 1 times 60, that works. It's even, so you can divide by 2. So 2 and 30 multiply together to get 60. Well, you can divide that by 3. 3 and 20 would work. Okay. 4 goes in there. 4 and 16 or 15. 5, it ends in 0, so you can go 5 and 12. And you just keep kind of working yourself kind of towards the middle here. 6 works, so you can go 6 and 10. That works. 7 does not go in there, and I think that's it. Now, basically, once you have them listed, you just say, all right, well, they both have a 1. That's a common factor. They both have a 2. That's a common factor. They both have a 3. Both have a 4. They both have a 6. They both have a 12. So that means 12 would be your greatest common factor. And that would be your GCF. Now, that's one method of doing that. But I'm not a big fan of that method because, as you can see, there's one problem that you could easily make a mistake. You just forget one combination, and you just miss one. If I missed the 3 times 12 here, or I missed the 3 times 20, something like that, or I missed the 5 and the 12, I may have not gotten to the greatest common factor. So it's really easy with this method of just listing them all out to make mistakes. So there's I think, a little bit better method of doing this, and that is to use prime factorization. So basically, you just do this. You say 24. Let's break that down. What does 24 break down into? Well, it's even, so you can divide by 2. 2 and 12. 12 you can break down into 2 and 6. 6 you can break down into 2 and 3. So 12 is the same thing as 1, 2, 3 2s. So you have 2 to the third, and then you have a 3. Okay? And then you do the same thing with a 60. Okay? 60, well, you can break that to 6 times 10. 6 breaks down into 2 times 3, and 10 breaks down into 2. Okay? Which means 60 has 2 2s, 1 3, and a 5. Okay? So you break those down just like we did before. Now, what you look for, what do they have in common? You just look at these two prime factorizations. And basically, I like to say, what do they both have at least? Well, they both have 2s. How many 2s do they both have at least? So the GCF would mean, well, this has 2 2s, this has 3 2s. They both have at least 2 2s. Okay? This one has 3, but what do they have in common? They both have at least 1 3. This has a 5, this doesn't, so they don't both have a 5. And now all you do is you multiply that back together. So 2 2s is 4. 4 times 3 is 12. So again, you get the same answer. This, to me, is a much more reliable method, okay? It doesn't take much time to break them down. once you have them broken down, it's pretty easy to find the answer. Let's try another example here. Let's take 18 and 27. 18, what are two numbers that multiply together to get 18? Could use 3 and 6. You could use 2 and 9. It doesn't matter. 9 breaks down into 3 and 3. So 18 is the same thing as 2, and then I have 2 3s. Okay? 27, well, 27 breaks down into 3 and 9. 9 is 3 and 3. So basically you just have 3 3s. So we're just looking at those two prime factorizations. And then the GCF will just simply be, what do these both have in common? This has a 2, but this doesn't. They both have 3s, so the question is, how many 3s do they both have? They both have at least 2 3s. 3 squared is 9, so the answer would be 9. 9 would be the biggest number that you can divide both of those two numbers evenly by. Make sense? So that's the GCF. So let's try a few. You can do it with letters and numbers. Again, it's the same kind of concept. We're going to break this 18 down. We'll just throw the g squared in the end. Okay? So kind of ignore that g squared for a second. Break that 18 down. 18 breaks down into 2 and 9. 9 is 3 and 3. So the prime factorization of 18g squared would be, I have a 2. I have 2 3s. And then I have 2 g's. Just write that right next to it. Okay? So 18g squared is the same as 2 times 3 squared times g squared. We do the same thing for 27g to the third, which would be, we got 3 and 9, 3 and 3. So basically 27g to the third means I have 3 3s and 3 g's. And then the GCF, again, what do these both have in common? They both have 3s. How many 3s do they both have at least? Well, this has 2, this has 3. They both have at least 2. They also both have g's, and they also both have at least 2 g's. So again, we just multiply that back together, and it would be 9g squared, and that would be the GCF, okay? So let's try another example. Let's say we have these two here. Again, we're just going to break that down. That 30 breaks down into, you can go 2 and 15, 3 and 10. 10 breaks down into 2 and 5. So this 30x squared y squared z would be the same thing as, I have a 2, I have a 3, I have a 5. There's only one of each. I have x to the third, I have y squared, and I have 1z. Okay, we're just looking at that. We do the same thing here with this 36. Well, 36 we know is 6 times 6, 2 times 3, 2 times 3. So I have 2 2s, 2 3s. I have x to the fourth, y to the fifth, and z to the third. And then again, when you go to do the GCF, all you're looking for is, what do these both have in common? They both have a 2. This has 2 2s, but this one only has 1. So they both have at least 1 2. They both have 3s. This has 2, this has 1, so they both only have at least 1. This has a 5, this doesn't have any 5s, so they don't have any 5s in common. They both have x's. This has 3 of them, this has 4 of them, so they both have at least 3 x's. They both have at least 2 y's, and they both have at least 1 z. Only thing left to do is multiply those back together. So the answer would be 6 x to the third y squared z. And that would be the GCF, okay? So give a few problems a try. Let me know how it works out for you. Again, like I said before, give this chapter a good try. These are some things that you will need in the next couple of years in math. So talk to you guys later.